Hi class, welcome back to our lectures on quantum field theory, and this is chapter 2, and we're on the second lecture on this chapter. By the way, along with this lecture, you can also read Michio Kaku, F. Mandel, and G. Shaw, and also F. Gross. They're all quantum field theory books. So earlier, in the previous lecture, we discussed about basic Lagrangian in classical mechanics, and we um, played on Euler-Lagrange equation to get the equations of motion of some systems, and then we dealt with about action, and from the action uh, we have derived the Euler-Lagrange equation for fields, where we selected the most possible path for a particle from one point to another. So in this chapter, we'll be dealing with symmetries and the conservation laws, because if you follow the first lecture, symmetries are actually consequences of I mean consequences of having the optimal path, meaning that you will have if you perturb the path, and if you let the path's perturbation equate to zero, then you'll get some symmetry, and this symmetry also gives you some conservation laws. So we will deal with this in this lecture. Symmetry is a perspective change that leaves the equation of motion invariant. And this change could be translational, or in time, or a rotation. And there are external symmetries which are dependent on the changes in space-time. There are also internal symmetries, changes in the fields that do not involve changes with respect to space-time at all. There is a very important theorem called Neuters Theorem. This allows to relate symmetries to conserved quantities like charge, energy, and momentum. So let's explore this as we go along with this lecture. In mathematical perspective, a symmetry is a kind of variation to the fields or the Lagrangian that leaves the equation of motion invariant. So no matter how you perturb the Lagrangian, the equations of motion are still the same. Two of the most important results of physics, conservation of energy and the conservation of momentum, are due to the results from a small displacement in space-time. Due to a symmetry that results from a small displacement in space-time. So suppose that you have a space-time coordinate that varies according to this one, where a mu is a small and arbitrary parameter describing the displacement in space-time. The x mu here is the space-time coordinate. So your changes in the field, if you expand it by Taylor series, your transformation would look like this. You take only the first order of a mu, because a mu is very small. So if you take the higher orders, it would just approximate to 0. So here it is. So here you have phi x, and then the transformed field expanded in Taylor series, taking only the first order or the first power of a mu. Under a small perturbation, the field can be described as this one here. This is also perturbation of the field, where of course your delta phi would just be equal to a mu partial derivative mu of phi. So since the Lagrangian depends only on the field and its first derivative, then the changes in your Lagrangian density is in this form. Derivative with respect to phi and derivative with respect to first order derivative of phi. From the Euler-Lagrange equation, where this is just the transposed Euler-Lagrange equation. Transpose meaning you change from one side to the other, not the matrix transpose. So you can write this delta of the, or the change in the Lagrangian density into this, knowing that you have this Lagrange equation. So you can replace this term and write it the way it's written here. So we can also interchange delta and the derivative here into this one. We can interchange that. It's a basic principle in derivatives. And you recall the integration by parts, and this is just integration by parts formula in the form of derivative. So if you take this one as this term as your f and your g as the change in the field, then you can rewrite this into this form. Into this form here. Note that we applied here this one as our change in the field, and note that the same index can only be used twice in a single expression, so we can change that into another dummy index so that you can write this as this one. Equivalently, the variation of the Lagrangian, considering how it varies directly with respect to the displacement, you can also write your change in the Lagrangian in this form. So you can equate these two expressions now. And so, with that, your delta L would have to be this one. or your change in Lagrangian would have to be that one. And then if you transpose this, transpose this term, to the other side, then this would give you this expression, or this would give you this expression, where of course a nu here is arbitrary, so it can be of any value. So therefore what happens is that you will have this expression here to be equal to 0, and this is what we call the energy momentum tensor. The energy momentum tensor here. So here we define our T nu mu as the energy momentum tensor, which is just this one here. And the derivative of T mu nu is equal to 0. This means that the energy and momentum are conserved. So note that T00 is just equal to this one here, and this is nothing but the Hamiltonian density. It is the energy density, and the equation, the time derivative of T00 is 0, reflects conservation of energy. The components of momentum density are given by this one here, where I runs over the spatial indices, and we can actually get the components of momentum of the field if we integrate each of these terms over space. That is, you have to do this integral. So for conserved currents, this is a consequence of the Neuters Theorem. So we apply this theorem to derive a conserved current and an associated conserved charge. So if we vary our field again by a very small amount, then it would just look like that. So it transformed to some field in another perspective. You have your field plus some changes, and then we require these changes to be 0, and if this is 0, and what comes out would have to be a conserved quantity, or that if the changes we require to be 0, then we have some symmetry, and that symmetry would imply a conserved quantity. So the variation in the Lagrangian will be this one again, and we'll show that the changes in the Lagrangian, or the change in the Lagrangian, is equal to 0. So again, since the Lagrangian is just a function of the field and its first derivative, the change would just be that one. Basic principles in calculus. So from the Euler-Lagrange equation, your term here, this one, is just equal to this by Euler-Lagrange equation. So you can rewrite the change in the Lagrangian to be in this form. which is just this one here. So if the Lagrangian, change in the Lagrangian is 0, then this will be true. And since this is just the derivative of some quantity, this now is a conserved quantity, and we call this the conserved current. This one here, the conserved current. And we term that as J mu. And of course, it's the derivative of J mu is just 0 because it's conserved, constant. So here is what Neuters Theorem says. For every continuous symmetry of the Lagrangian such that a variation in the field that leaves the form of the Lagrangian unchanged, there is a conserved current. So there is a conserved charge as well if you calculate or if you integrate the current, and you can find that by integrating the time component of J. So here it is. Now let's go to the electromagnetic field. The Maxwell or electromagnetic field tensor is given by this one. So this is just denoted by or represented by F mu nu, and F mu nu is just the partial derivative of the vector potential A minus a partial derivative mu A, partial derivative nu A mu. And anyway, these are just the elements of the matrix of F mu nu. So you have a 4x4 matrix here. So in this case, you have, so for F 2 3, for example, you will have here 2 3 would be 2 negative bx, and this is just equal to partial derivative, I mean first derivative of not first derivative, but yeah, first derivative with respect to y of a nu minus the partial derivative with respect to z of a mu. So that's how you get 232 is actually for y, and 3 is for z. So here the a mu is a 4 vector potential whose time components is the scalar potential and whose spatial components is the usual vector potential used to write down the magnetic field. So your a mu is of this form, and F mu nu satisfies or leads to the Maxwell's equation. Note that your F mu nu is antisymmetric. So if you get the transpose of F mu nu, you get a negative F nu mu here. Without the sources, the homogeneous Maxwell's equation can be written in terms of the electromagnetic field tensor here. And the inhomogeneous Maxwell's equation can be written as this one. So let's now go to an example. Show that the Lagrangian L, by the way, this is supposed to be L, and your L, the Lagrangian density, is negative 1/4 F mu nu minus J mu A mu. They show that the Lagrangian L leads to the inhomogeneous Maxwell's equation if the potential is varied, leaving the current density constant. So we write down an equation as an integral of the Lagrangian density, which is this one. This is your Lagrangian density, and the variation of the action would be this one, computed in terms of the variation of the vector potential. So you will have this as the variation. Here you have a constant or a conserved current, so the derivative of that would just be equal to 0. So you will only have the derivative of this part here. So for the first term, we use the definition of the electromagnetic field tensor, which is this one. And to get the derivative of that, of this one here, we will have this. Okay, we will have that. And if we integrate by parts to transfer the derivatives from here to here, we do integration by parts, and we will see that this is just equivalent to this one, this expression here. So now again, repeated indices are dummy indices, so mu and nu can be swapped in the second term. Giving us this one here. So now, using the antisymmetry of the electromagnetic tensor under the interchange of the indices, this will get the minus sign on the second term. It makes it positive, since your F mu nu is just equal to negative F mu mu. So you will have this as a result. You have that as a result, and so therefore your first term here, this term here, would be equal to this one. So for the second term, which is this one here, will involve the erasing of the index of f. I mean the index, yeah, index of f. In which case you have to raise the index mu nu, so that we will have this one. So now we're going to put f rho sigma inside the parentheses, and then doing integration by parts, we will be able to show that this is equivalent. And now we're going to lower the indices on the derivative operator to get this one. This one being equal to this. And now doing the same for the vector potential will give us this. Now repeated indices are dummy indices, so the labels can be changed. And focusing on the second term, we can change rho to nu and then sigma to mu to obtain this one. And applying this antisymmetry of the electromagnetic tensor to the second term to get rid of the minus sign, we will have this. And then relabeling the first term again, let rho to mu and then sigma to mu to get this one. And so finally we will have this one. So therefore the variation of the action becomes this. So now the variation in the action must vanish, and since this one is arbitrary, so the whole integral would only be 0 if the integrand is 0 everywhere in the domain. So therefore we will have this one, which is just the equation we expected. So the action will only vanish if Maxwell's equations are satisfied. So now let's go to gauge transformation. Here is a brief introduction to invariance through gauge transformation. The idea of gauge transformation follows from studies of electricity and magnetism, where changes to the scalar and vector potentials psi and A can be made without changing the fields equation, and hence the physical fields electric field and magnetic field. Recall that the magnetic field can be written in terms of the vector potential A using the curl relation, and we also know from electromagnetism that this one is true. The divergence of the curl of F is equal to 0 for any vector field F, so that the divergence of V is 0 is still satisfied for B equal to the curl of A. Now, if we let F be some scalar function and define a new vector potential such that our new vector potential A prime would be A plus del F. So we note that the curl of a del of a function is always equal to 0. Hence, a term of the form del F can be added to the vector potential with impunity and convenience. The magnetic field B will remain unchanged. So here. So as shown, the magnetic field is unchanged by the transformation of the form A prime equals A plus del F, and this type of transformation in electrodynamics is a gauge transformation. And there can be different choices for implementing a gauge transformation. So for example, if we require that the divergence of A is equal to 0, this is called Coulomb gauge. And if we have the divergence of A equal to mu sub O epsilon sub O partial psi with respect to T, this is called the Lorentz gauge. So in quantum field theory, a similar notion is also applied by considering transformation to the field that leave the Lagrangian invariant. So this is called gauge transformation. So now we will consider the Klein-Gordon Lagrangian with a complex field, this one, and we let U to be a unitary transformation applied to the field such that U does not depend on space-time. So we let our field transform into U phi. Then of course the adjoint of that will just be equal to this one. So look at this. If you get the adjoint, you would have an interchange of U and phi. The transformation is unitary, so therefore you will have this one. So this is the transformation of the first term here. But here U does not depend on the space-time, so the derivative operators do not affect it. Thus, you will have this. And now similarly for the second term, would be very trivial, and it would just be this one. So under that transformation, under this one here, under this one, this Lagrangian is invariant. So since u is a constant, it can be written since u is a constant, you can write it in the form u equals e to the lambda, e to the I lambda, where lambda is a constant. By the way, lambda can also be a matrix for as long as it is Hermitian. This means that lambda is equal to lambda adjoint. So since this is a constant, the gauge transformation in this case is a global. This does not depend on space-time. There's also a local gauge transformation, which of course the gauge depends on the position or the space-time. I mean, this is more of interest in particle physics. The local gauge transformation that are of interest are the local transformation that depend on space-time. This type of transformation satisfies the requirements of special relativity, and that is, nothing can be traveling faster than the speed of light. So recall our transformation. Now this time consider u to be a unitary transformation, but let it depend on the space-time, so that it is a function of space-time. So this means that the terms partial mu of u will not vanish. So how does the Lagrangian change by the transformation here? Would it look like, would it give a result that looks like this? Will it give? But anyway, let's continue. So it is trivial for the second term. It preserves the second term. The first term, however, will change due to the space-time dependence of u, so that your transformation, this term will be there will be an extension for that term, since it is a function of space-time. And also this one here. So exploiting the fact that u is unitary, so our transformation of the field, which is this one, and this one is just equal to this, and this is just equal to identity, so you can multiply it anytime. So you have here u, and you can actually interchange this with the U adjoint, so that I'm sorry about that. You will have this term here as this one, and that this term will be just here. So you can multiply identity here. Doesn't affect, it's just an identity matrix. To maintain the invariance, we have to get rid of this. And to do this, introduce a new object, a space-time dependent field A mu, which is a function of space-time. We call that the gauge potential, a hidden field to keep the form of the Lagrangian invariant. And this will also lead us to introduce a covariant derivative that acts on the field, as this one here. This is called the derivative operator that keeps the Lagrangian invariant under a local gauge transformation. So recalling the effect of a global gauge transformation here, this gave your partial mu of field to u partial of the field. So the covariant derivative, which is this one, recovers the same similar result in the case of a local gauge transformation, and this will lead to your covariant derivative of your field to this. And this can be accomplished if your A mu is defined such that it obeys the similarity transformation, which is this one. So let's now go to an example. So the example here is: consider a charged scalar particle of mass m with charge q, and describe a suitable modification of the derivative operator that will yield a Lorentz invariant real Lagrangian. So here, the field equations for a complex field corresponding to a charged scalar particle are obtained using the covariant derivative in 2.40. In this case, we write this in the form, that one, the derivative, transformation of the derivative. So now our Lagrangian would be this one. And this variation of the Lagrangian leads to the equation of motion, which is just equal to this. So this would just be also equal to I mu minus q a mu here, this one here. So that's about it for this lecture. I hope you got something about gauge transformation, and of course the conserved quantities from symmetries. So the next lecture would be chapter 3, and that would be on introduction to group theory. Stay tuned.